Hey everyone, today I'm here with one interesting topic called privacy attacks. So let me explain you in a layman language. Your machine learning model is leaking your training data right now. Whether you know it or not, in 2021, researchers extracted real email address and phone numbers from GPT-2. In 2023, in the same way, GPT was caught regulating memorized private conversations. Today I'm going to show you how exactly these privacy attacks works and more importantly how to define against them. So this is a membership inference and model inference like the privacy attacks explanation. So let's get started. Here's the fundamental issue. Machine learning models remember their training data. That's literally how they work. They learn patterns from examples, but this memory creates a vulnerability. Attackers can exploit this extractive, sensitive information in two ways. Let me explain you those two ways. So the first one is membership inference. So how it works is like determining if a specific person's data was used to train the model. Was this patient in the HIV study, or was this patient or the person in the criminal database? So this model's predictions reveals the answer. And coming to the second one, model inversion. So it is like a reconstructing what the training data actually look like from a face recognition model. So you can recover the faces. From the medical model, you can extract the patient's data records from a language model. So you can extract the memorized secrets. Let me show you what these attacks look like. Yeah, here you can see. Membership inference exploits a simple insight like the models are overconfident on the data they have seen before. If I show the model training data, it predicts with high confidence. If I show it new data, the confidence level is lower. This is the difference which leaks the information. So, let me give you an example. Imagine a hospital builds a model to predict disease risk. An insurance company wants to know if Alice was in the training data set. Because being in the disease prediction training set suggests she might be high risk. So they query the model with Alice data. If the model is very confident in its prediction, then Alice was probably in the training set. So if it's uncertain, she probably wasn't. So this violates the privacy. Like Alisa never consented to reveal whether she's participated in this study, but the model is leaked it anyway, right? So in the same way, there is one more called model inversion. So this model inversion is even more severe. Instead of just knowing someone was in the training data, you can reconstruct what their data looked like. Here's how it works. You query the model thousands of times but carefully with the chosen inputs. So using the model's response to gradually reconstruct the training data, it like reverse engineering a recipe by repeatedly testing the dish and adjusting the ingredients. Eventually you recover the original data, or that too in our case the original training data. So let me give you a real example. In 2020, sorry, in 2015, researchers successfully reconstructed face from a face recognition model. In 2021, they extracted email addresses, phone numbers, and personally identifiable information from the GPT-2. So aren't theoretical attacks; they have been demonstrated on the real models. Okay, enough theory. Let's actually perform these attacks practically. Let me walk you through the code. So, yeah, here's the code. So, for our demonstrations, I have built a simple medical diagnosis classifier which predicts whether a patient has a this is based on the symptoms like test results and demographics. I'll train it on 1,000 synthetic patient records, then attack it. So, here in this, like nothing fancy here, it's a standard neural network the two hidden layers, ReLU and activations, and the train with a basic SGD. So this is a kind of model you had used in the production everywhere. So which makes it vulnerable. So here we are training on 7,000, sorry, 700 patients, testing on 300. So the model achieves 92% of accuracy, which is pretty good. But the problem is it's achieved 94% of accuracy on the training set, but the 2% gap means it's slightly overfitting. So then memorizing the training data, and that memorized is exploitable. And moving on to the next one, let me show you the one more attack called membership attack. So here now let's perform a membership inference attack. So here our main goal is to like given a patient record, like they are already given a patient record, so we need to determine if it was in the training set or not. So to do that, here's a strategy. Like we are going to use what's called a shadow model approach. We train multiple shadow models that mimic our target, which use these shadow models to learn the difference between how the models behave in the training data versus the test data. So then we build an attack classifier that predicts membership based on these patterns. So we are training with the five shadow models, as I said, on the similar data. Each shadow models learns the same task. For each shadow model, we know like exactly which data points were in the training set and which aren't. So this gives us the label training data. So yeah, and in this results you can see the attack achieves 73% of accuracy at identifying the training set members. That's way better than the random guessing, like which would be 50%. This is a privacy leak. So let me be clear about what just happened. By only querying the model's API, no access to the training data. So we determined with 73% of accuracy whether specific patients were in the training data set. So the information is supposed to be private. It's not anymore here. So let me go with the one more attack called inversion attack. So in membership inference tells us who was in the training data. Model inference tells us what's their data look like. Let's reconstruct actual training samples. So this attacks uses a gradient descent. So we start with a random noise, completely meaningless data. So then we repeatedly query the model asking, does this look like a patient with a disease? Or we use the model's confidence to guide our search. So let me run this and show you what will gonna happen. It's like a game of hot and cold. The model says warmer or colder, and we adjust our fake patient record accordingly. Like after thousands of queries, we reconstructed something that looks like a real training sample. So, with the results, you can see that like watch those laws decrease. Like we are getting closer to something the model recognizes as a simple, and that too as a training sample iteration like 200, 400. Yeah, so the model is getting more and more confident that our reconstructed samples looks like real training data. And let me talk about the defense strategy from now. So in that, the first one is differential privacy. So this differential privacy is a gold standard, like we can say that it provides the mathematical guarantees any individual's data has limited impact on the model's output. So the key parameter is ellipson. The lower ellipson means the stronger privacy. And we implemented this using DPSJD as I said earlier. So differentially, the private stochastic gradient descent. So during the training, we clip the gradient per samples to limit the individual influence, and then we add that calibrated Gaussian noise. So the noise makes the contribution of any single training sample. And then, yeah, you can see, let's like after training the models. Here's the privacy ultra trade off in action. With Ellipson 1, we get the strongest privacy, but privacy drops from 92% to 84% and 8% of cost with ellipson 3. So we only lose 3% of accuracy with the ellipson 10 and in just 1%. So the key thing here in this is a fundamental trade off privacy but cost accuracy. So the question is like how much privacy do you need and how much accuracy can you afford to lose this? So for the medical data that 8% might look be worth it, for spam classifier probably it may not. So we have one more method. I'll show you that method too. That method is called the regularization. So yeah, here like you can see what are all the outputs I'm getting. So yeah, and let me walk you through the one more defense strategy. That is a second defense strategy, which is called regularization. Yeah, here you can see the impact on overfitting, like how the privacy impacting here, the normal user behavior and how many queries are allowed for the normal users, and then the pattern detection, analyzed queries, and how many queries are analyzed totally, which has high risk volumes and synthetic sampling and all. Yeah, you can see the confidence calibration here. The temperature scaling is like that is an higher temperature. Yeah, let me walk you through the regularization first. So, regularization doesn't give formal privacy guarantees, but it's a practical and effective. The idea is simple. So, basically, this is like prevent overfitting. To prevent the overfitting, we use this regularization because in the earlier method, we found a lot of overfitting there. So, it's like if your model doesn't memorize the training data, it can't leak the training data. So we apply three techniques here. L2 regularization to penalize the large weights, dropouts, and randomly disable neurons during the training. And early stopping is to prevent the training too long, like stopping the training earlier. All of these reduce the memorization. So as you can see the output, like with no regularization, we see large train test gap that is around 94% of training and accuracy and 92% of test accuracy. So that 2% gap is overfitting memorization. As we increase the regularization strength, the gap shrinks. Like the strong regularization brings us down to around 0.5% of gap. So the beautiful thing in the regularization is we only lose 1 to 2% of accuracy. Compare that to the DPs of 8% loss. So regularization is a cheaper defense through without mathematical guarantees. If your model generalizes well, it's hard to attack. Then the membership inference attack we ran earlier on a strongly regularized model, its accuracy drops from 75%. So this model inversion correlates the drops from 0.78 to 0.45 significant improvement. So next moving on to the next defense called query monitoring. So the first two defense protect the model during training. Query monitoring protects it during the deployment by detecting and blocking active attacks. So these three techniques here, first rate limiting, limit how many queries each user can make. Model inversion requires thousands of queries. Like rate limiting makes it impractical. So the second pattern detect, look how like for suspicious queries, patterns like repeated similar queries or sampling. And the third one is confidence calibration. Reduce the model's overconfidence and make membership inference harder. So, the scenario 1, the normal user makes 50 queries or an hour. No problem, all allowed. Scenario 2 is attacker tries 150 rapid queries for a model invasion attack. Boom, blocked at query 101, rate limit exceeded. So, In summary, it says that query monitoring won't stop a determined attacker and with insider access. So, coming to the next one, privacy matrix. So this is like a central tension in ML privacy in this. So more privacy means less accuracy, and more accuracy means less privacy. There is no free lunch. Let's quantify this. So with running this, we can see that we measure the privacy on like 0 to 100 scale. The baseline model no defenses scores 25 out of 100. So very poor privacy, membership inference is 73 accuracy, and the model inversion is 0.78 correlation, but accuracy is 92. So with the differential of this privacy at the ellipse, one privacy score is just jumped to out of 85 to the 100. I hope you got the clarity on this. Let me show you theoretically. So, as I said, this membership inference attack, in this, we were training the five shadow models, as I said, and like after training the attack classifier, it learns to recognize the patterns, indicate the membership. So, I confidence plus certain the prediction characteristics usually means in the training set with the lower confidence, the patterns means not in the training set. So yeah, so basically this achieves the accuracy around the 50%. So that it means like the 50% in the sense there must be a privacy leak, and the above 70% is nothing but a severe leak. So yeah, next moving on to the next attack as I shown in the demo, model inversion. So this start with a random noise. So if I can give you the clarity, the membership inference tells who was in the training, but in case of the model inversion, it tells like what their data is look like how the data is to be lived. And yeah, so this uses the gradient descent, like starting with a random noise, then like querying the model for the target class, then it uses the gradient model to optimize the input, and then iteratively refine the model to match the training data, and then it extracts the sensitive features from the window, and the results is like we get the reconstructed that something looks like a real training sample. So next, coming to the defense for these attacks, the first one is, so yeah, in this differential privacy we have used stochastic gradient descent. So during this training, we clip gradients per example to the limit individual influence, and then we added the calibrated Gaussian noise. So that noise masks the contribution of any single training example. So mainly the fundamental trade-off is like the privacy cost the accuracy. So let me give an example. The question is how much privacy do you need and how much accuracy you can afford to lose. Like that it may happens. So yeah, moving on to the next defense called regularization. So this doesn't give any formal privacy guarantee, but it's like practical and effective. So the idea of this regularization is very simple, like preventing the overfitting. So if we can see that like in the before defense, we have seen the overfitting is like more than the results. So in this regularization, so basically this regularization prevents the overfitting. So here we applied three techniques. First one is L2, that is like L2 regularization to penalize the large weights. And next one is the dropout, that to randomly disable the neurons during the training. And the third one is early stopping, that to prevent the training too long, like stopping the training earlier. So all of this reduce the memorization. And then moving into the next defense, which is called the query monitoring. Nothing but the model monitoring. So the first two defenses protect the model during the training. So this model monitoring protects it during the deployment by detecting and blocking any active attacks. So the three techniques here is like first one is rate limiting. Like it shows how the limit like limits the how many queries each user can make the model, and the model inversion requires thousands of queries like that. Yeah. And next one is blocking the gradient access. So this is all about the model monitoring, and this won't stop a determined attacker with insider access, but it dramatically raises the bar for the external attacks. And yeah, here's the defense comparison, like what all the three defenses does. So let's compare this. Differential privacy, that is the strongest protection, formal guarantees, and but the 5 to 6% of accuracy cost. And next one is regularization, that is good protection but minimal accuracy cost 1 to 2%, which is better than the differential privacy, but it doesn't guarantees. And next one is model monitoring, that catches active attacks with a zero training time cost, but reactive, not the preventive. So for most systems I recommend layered defense. Use the regularization as your baseline. Why? Because it's cheap and effective too. So add the DP if your data is highly sensitive. I mean, the differential privacy. If your data is sensitive, then add that. So, the medical records, financial data, or anything regulated, and always add monitoring in the production to detect attacks in progress. So, yeah, already you have seen the privacy matrix demo also. So, like how all this works and with the real metrics. So let's wrap up with practical checklist for protecting the ML models. So first, like whatever we have learned is accessing your data sensitivity before the training. Not at all models needed the same level of protection. A spam classifier doesn't need what the medical diagnosis needs the model. So using stochastic gradient descent for the high risk data sets, it's worth the accuracy cost when the data is truly sensitive. Always apply the regularization, drop out L2 and early stopping, which are under the regularization. So it's practically free privacy improvement. And limiting the model confidence in outputs is like over confident models leak more info, like rate limit your APIs. No legitimate user needs thousands of queries per an hour. And monitor the queries patterns and block the suspicious behavior. And crucially, avoid exposing gradients publicly. So the model inversion attacks are much more effective with the gradient access. If you must expose them, much more effective with a gradient access. Then, for instance, in federating the learning, add the noise. And when it comes to regular privacy audits, run the own attacks, like your own attacks if you can do it. So can an attacker find the vulnerabilities before they do? So, and the next one is adding the document to your privacy measures. Like when the regulators comes asking, somehow like show them your DP ellipson, your regularization parameters, your monitoring logs. So the document is protection. So it's better to make the document whatever you have the privacy measures what you have done. So moving on to the end, let's recap. ML models leak the training data through their predictions. So that's not a bug, it's a fundamental to how they work. And membership inference reveals who was in your training set, and model inversion reconstruct what's their data is look like. And both are real threats demonstrated on the production system. But we have defenses, like differential privacy provides the provable protection at an accuracy cost. So the regularization provides practical protection cheaply, like monitoring detects active attacks, and using all three in the layers. So the privacy is machine learning isn't optional anymore, like for the GDPR, CCPA, and HIPAA regularizations are catching up. but behind the compliance, it's the right thing to do. So your users trusted you with all their data, so protect it. So yeah, all the code from today, the attacks and defenses is in the GitHub repository. So try on your system by running these attacks. So let's see how much they leak, then fix it. So the private problem isn't going away, but we have the tools to address it. Use them.